Okay, so here we are for the last part of my lectures in this series, looking at reaction mechanisms. So where we got to in the previous lecture was we'd seen the different elimination reaction mechanisms, E1 and E2, and we'd said how these can compete with each other, but they can also compete with SN1 and SN2 reactions. So what we're going to do in this last part of the series is just think, how could we influence the reactions so that we get elimination over substitution or substitution over elimination? So obviously these reactions give very different products. The elimination reactions give access to alkenes, whereas the substitution reactions give access to aliphatic molecules, which would have different functional groups based on the nucleophile that we've been using. So the reason that these can compete is because the reactive part of a nucleophile is the same as the reactive part of a base. It's an unshared electron pair, it's a negative charge, it's something which is electron rich. So therefore, all of our nucleophiles are potentially bases, and all of our bases are potentially nucleophiles. So those components are essentially very similar, and they can do different reactions dependent on the reaction conditions, the different reactions being substitution or elimination. So if we wanted to bias the reaction so that an elimination occurred or a substitution occurred, what we can do is actually think about the basicity of the negative component, the nucleophile, which is undergoing the reaction. And what we find is the more basic the nucleophile, the more likely elimination is to occur. The reason for this is that strong bases, they like to pull off protons to give a neutral molecule rather than attack carbon atoms. And if it's pulling off a proton from a substrate, then that's going to, after we've lost the leaving group, lead to the alkene. So I've got an example here where we've got exactly the same substrate. So here, this part here is a tertiary butyl. We've got a methyl here, we've got a methyl here, a methyl here on a carbon. And onto this, we've got a chlorine as the leaving group. So this tert butyl chloride is the same molecule as we've got in this reaction. But what is different is the nature of the species with which we are reacting this tert butyl chloride. So in this case here, we're just reacting it with ethanol, whereas in this case here, we're reacting it with ethoxide. So basically the anionic form of ethanol. And this here being negatively charged, this is a much stronger base. So ethoxide is a much stronger base than ethanol. So in this case here, ethoxide is going to want to pull off a hydrogen because it's basic, whereas this here, there's no reason it wants to pull off a hydrogen. If it did pull off a hydrogen from the molecule, it wouldn't make this any more stable. Whereas if this pulled off a hydrogen from the molecule, it would convert it, instead of being a negatively charged species, through to something which is neutral to ethanol. So this side here, when this reacts with the tert butyl chloride, the ethoxide is going to want to attack a hydrogen. In this case here, when our ethanol attacks the tert butyl chloride, it's going to want to attack the carbon. There's no benefit to it pulling off a hydrogen. So in other words here, because it's going to be acting as something which attacks carbon, it's going to be reacting as a nucleophile rather than a base. It will attack the tert butyl with the loss of the chloride. It's likely to be via an SN1 reaction because this can form a stable carbocation. So here we'd be getting a nucleophilic substitution reaction. So our nucleophile, being the ethoxy part of the molecule, would displace the chloride so that we'd get ethoxy within our molecule. We've got an aliphatic molecule. It's a nucleophilic substitution reaction. In this case here, as we said, ethoxide as a base wants to pull off hydrogen so that this would be converted to a more stable molecule rather than a negatively charged anion, so it would be converted to ethanol. And the way it can do that is to pull off a hydrogen from any of these neighbouring methyl groups. All of these are equivalent. But let's imagine if we had a hydrogen up here, the ethoxide come in, pull off the hydrogen, kick the electrons round, kick out the chloride. So then, because it's an elimination reaction, we'd be making the double bond across this position as shown here. So we would be making the alkene. So in terms of how do we bias elimination versus substitution and vice versa, what we're saying is if we have an ordinary nucleophile which isn't a strong base and it's not negatively charged, we're more likely to get a nucleophilic substitution reaction. If we have something which is a strong base, so for instance in the anionic form, then that's more likely to do an elimination reaction and to make an alkene. Okay, so that's one way that we can influence the reactions, looking at the nucleophilicity and the basicity. The second thing that we can do is think about the size of the nucleophile. So here what we're thinking about again is if it's a nucleophilic substitution reaction, then our reactive nucleophile has to be able to attack the carbon because it has to form a bond to that carbon when the leaving group departs to do the substitution part of the reaction. For the elimination, what we want to do is pull off a hydrogen. We don't need to be able to get to the carbon before the leaving group. We don't need to be able to get to the carbon as part of the displacement of the leaving group. So if we were, for instance, to have something like this, potassium hydroxide, this has got a small counter ion to the K+. So potassium is going to be K+. This would then be OH-. If we compare it with this case here, again, we'd have K+, and here we'd have OT-butyl-. So remember here we had the T-butyl, so it's basically a carbon with 3 different methyl groups is a T-butyl. So what we're saying here is on that bulky T-butyl would have the oxygen minus. So this here is obviously much bulkier. That oxygen with the carbon with 3 different methyl groups on is much, much bigger than the OH, which is just the oxygen with the H on. So if we would have something like this, which is quite small, that should be able to access a carbon to do a substitution reaction. However, in this case here, where it's very bulky, it's going to be very hard for that to access the carbon because it's got other groups along here. We're going to have a lot of steric hindrance. So for this to be able to squeeze by and attack the carbon is going to require quite a lot of energy, making it disfavoured. So therefore, if it's disfavoured, for it to be able to attack the carbon, it's still reactive, it wants to do a reaction, it's going to try and pull off a hydrogen from the molecule. So for instance, at this position here, where the hydrogen isn't then attached to the carbon, it's more accessible, there's less steric hindrance. So just to recap what we mean, what we're saying is if we have a small nucleophile that should be able to access a carbon and do a substitution reaction. So in this case here, nucleophilic substitution reaction, we've replaced our bromide with an OH. In contrast, if we were to use a very big negatively charged species, then that's so big that it's not able to actually access the carbon. There's too much steric hindrance, that would require far too much energy. So instead, it's going to access a more sterically accessible area, such as a hydrogen. And when it does that, we'd have the hydrogen removed, we'd have the leaving group removed, we'd be doing an elimination reaction, which would give us an alkene. So to influence whether we get a substitution reaction or whether we get an elimination reaction, we can alter the size of the nucleophile. The smaller the nucleophile, the more likely we are to get a substitution reaction. The larger the negatively charged species is, the more likely we are to get an elimination reaction to give the alkene. So I've discussed in words and with a little bit of laser pointer annotation how this reaction goes, but I just have got another exercise for you to try here. I'd like you to draw the curly arrow mechanisms for the above reactions. So I'd like you to think, for this case here, if this was to react with K+, OH-, what would the arrows be to get us through to this alcohol product? And I'd like you to think for this potassium butoxide, so this is a bulky base, the T-butyl, we saw here a carbon with 3 methyls. I'd like you to think in this case where you've got that T-butyl with the oxygen minus, how is that going about the mechanism to convert this same molecule as here through to the alkene in this case. So have a go at that. Hopefully you can have a first attempt at it. And then I've given you this accompanying video again so that you can see the worked answer for this question. Okay, but that's given us two options to influence elimination over substitution and vice versa. We can look at the basicity of the nucleophile. We can look at the size of the nucleophile. And the last thing we can do is when we're doing our reaction, we can also alter the reaction temperature. So that's very easy to do in the lab. You can just use solvents which have different boiling points so that when you heat them, the reaction mixture is then occurring at different temperatures. So why is it important to think about the temperature? Well, the temperature is going to have a big effect if we think about the entropy change of a reaction, because this equation here, Gibbs free energy equation, tells us if we want the reaction to be favoured, we want a negative delta G, and to influence the delta G to be negative, we can look at this component here. We can look at the T delta S, where delta S is the entropy change. So if we were to have a given entropy change, and if we were to multiply it by a high temperature, then the bigger the entropy change multiplied by the higher temperature is going to give us a larger T delta S component. And because that's negative in this equation, the larger this is, the more negative delta G will be. And the more negative delta G, the more favoured the reaction. So by altering the temperature, we can make this a significant factor in the Gibbs free energy equation. The temperature is multiplied by the change in entropy. So what we can also do is we can think about the entropy change for the nucleophilic substitution reaction and compare it with the entropy change for an elimination reaction. So for entropy change, what we're looking at is the amount of disorder which is occurring in the reaction. How much chaos, how much disorder are we forming in the reaction? And if we look at a substitution reaction, we've got two components on the left-hand side. We've got the nucleophile and we've got the substrate. And when we do our substitution reaction, whether it's SN1 or SN2, doesn't matter. We end up with two components on the right-hand side of the equation. We end up with our substituted product and our leaving group. So in other words, two molecules of starter materials give us two molecules of product. We're not creating any extra molecules, we're not increasing the entropy of the reaction. In contrast though, if we were to look at our elimination reactions, and again I've drawn it here for E2, but the same would be said for E1. On the left hand side we've got our base, we've got our starter material, so we've got two molecules. But when we've done our elimination reaction, our base has pulled off the hydrogen to give us one molecule. We've made our alkene, that gives us the second molecule, and we've kicked out our leaving group, which gives us our third molecule. So for elimination, we've got two molecules on the left, giving us three molecules on the right. So we're creating more molecules from our reaction than we had in our starter materials, and so therefore we are creating entropy, we're creating chaos. So for the elimination reaction, the delta S is going to be larger than for the substitution reaction. So if the entropy is larger for elimination and we multiply it by a higher temperature, that's really going to make this a very significant term in the Gibbs free energy for making delta G negative. And if it's negative, it's going to be more favoured. So to put that into context, what we're saying is if we increase the temperature of the reaction, we're more likely to get an elimination reaction occurring than we are a substitution reaction. So again, that's a very easy way for us to influence our reaction. So we get more of the elimination occurring rather than the substitution, and we get more of the alkene forming. Okay, so just to summarise, we're nearly finished. We've just got a couple more slides to do. So just to summarise from this part, we've gone through reaction mechanisms step by step, and we've looked in particular at the SN1, the SN2, the E1 and the E2 reactions. So please do make sure you can draw out and you understand the generic reaction mechanisms that we have gone through for each of those, the SN1, SN2, E1 and E2. What we've also done is think about conditions that can favour, for instance, an SN2 over an SN1 reaction or vice versa, or an E2 over an E1 reaction or vice versa. When we did that, we thought about the nature of the the intermediate or the transition state and the factors that might stabilise that. What we've also done in these slides from this part of the lecture is we've also looked at how we could favour substitution reactions over elimination reactions and vice versa. So I should just say here what we're talking about is favouring. So it's very, very difficult in the lab to do a reaction that would just give you one product. Often we will still get mixtures, and then the challenge is how do we separate that mixture, how do we check what we've got in that mixture. But you'll be learning about that in analytical chemistry, chromatography methods and spectroscopic methods for how we characterise them. For instance, I know you're looking at things like UV with Dr. Hall, so all of that would help us in terms of how we know what we've made. But here the challenge is we are going to get mixtures of products, but we can influence how much we get so that we can favour one type of product over another. What we've also looked at, obviously, are the stereochemical consequences. So we've seen that SN1 reactions generally produce racemic mixtures. Remember, the definition for that means that we get equal amounts of each enantiomer. In contrast, SN2 reactions are going to give us single isomers if we've got a single isomer of starting material. That isomer will have inverted stereochemistry due to the mechanism. So because we get a single isomer of product from a single isomer of starting material, we call the SN2 reaction stereospecific. So make sure you're happy with that definition for stereospecific. In terms of stereochemistry for the E1 reaction, we saw the E1 reaction are stereoselective. So although we get a mixture of the E and the Z alkene, we tend to predominantly form the E alkene. Again, we looked at the reasons for this in the mechanism. When we go through the carbocation, we can get rotation around the carbon-carbon bond to give a more stable form of the carbocation with less steric hindrance. We've also looked at the stereochemistry of the E2 reactions. That's where we first introduced that definition, stereospecific. And so we've seen there, based on that definition, that the stereochemistry of the starter material will influence the stereochemistry of our product alkene. And therefore, if we choose one particular diastereoisomer, we should be able to direct whether we form the E or the Z alkene. And we looked at some specific examples for that. So that's great. If we wanted to make alkenes using an elimination reaction, we know that we could make a mixture of the two using the E1 reaction, or we can make a single isomer if we use a single isomer of starter material. But in some cases, we don't have the right starter materials to be able to make the alkenes. Perhaps we need particular functional groups within that alkene starter material, and we aren't able to access that. So it's just useful to always think of complementary reactions. So I just wanted to finish this because we've been looking at alkenes, and because the next lot of lectures that look at reaction mechanisms with Dr. Brazier will be looking at reactions of alkenes. I just wanted to finish by giving you another way in which we can make alkenes based on completely different starter materials to those that we use in the elimination reactions. So the starter materials that we're going to use are alkynes. So remember, alkynes are molecules where you have a triple bond. They've got a linear structure. You'll have looked at this with Dr. Sarah Allman. So a way that we can make the alkene from the alkyne is to add hydrogen to the alkyne. And in particular, if we were to have the hydrogen coordinated to a catalyst, so this wiggly line here is a metal surface, that's going to be a catalyst to which hydrogen can be absorbed. That can add to the alkyne on one face of the alkyne, and if it adds to one face of the alkyne, it's going to give this here. It's going to give us the Z alkene, the cis alkene, because the hydrogen has been added to the same side. So if we ever wanted to make this Z alkene, we could look to do it from an alkyne by adding hydrogen under particular conditions using a particular catalyst. So you wouldn't need to know the details of the catalyst. It's got a palladium, it's got a lead, and it's got a calcium component. The point you should know, though, is that that catalyst has to be poisoned. What we mean by poisoned is it can't just be a straightforward palladium catalyst, because if we were to use just a straight palladium catalyst, we would add our hydrogen to the same side of the alkyne to make the alkene. but that palladium catalyst is still effective at doing a further reduction of the alkene. More hydrogen could add to the alkene to give the alkane. That's a useful transformation, but not in our case where we're wanting to make alkenes. So if we want to make an alkene and we can't do an elimination reaction, and instead we're going to add hydrogen to an alkyne, what we'll do is we'll add it in the presence of a poisoned catalyst. You don't need to know the details of that poisoned catalyst. Just be aware though, it has to be poisoned. It cannot be the free palladium carbon catalyst, because that would do a complete reduction down to the alkane. Okay, so that reaction would give us access to the Z alkene. It's also useful to think, how has this been used? Has it been used in examples that are therapeutically useful? So again, please don't ever think you'd have to draw this molecule out. But what I'm showing you is that this is a complex molecule and it's got an alkyne and it's got an alkene. And in the presence of hydrogen and a poison catalyst, this is a slightly different poison catalyst, but it's poisoned, so we know what we're going to do is only be able to reduce alkynes. So we add our hydrogen to the same side of the alkyne to give the alkene. This wouldn't be further reduced because the alkene, this wouldn't be further reduced because the catalyst is poisoned. Likewise, this alkene here in the starting material would not be reduced because we've got a poisoned catalyst. This is interesting from a therapeutic point of view because these prostaglandins, these are useful. These are lipids that are made at the sites of tissue damage or infection, and we can try to make analogues of the prostaglandins to control inflammation. So this is a classic example of a prostaglandin synthesis which came from a Nobel Prize winner, Stork. So just to recap, if we want to make these Z alkenes, we can do it from alkynes by using hydrogen and a poisoned catalyst, and here's a specific example. So just again for completeness, we might, rather than wanting to make Z alkenes, we might want to make E alkenes, and again we can do this from alkynes. What we do in this case is use very different conditions. You would not need to know these conditions, but just be aware that there are conditions through which you can take these alkynes through to the E alkenes. So now we've got the hydrogen, the lowest priority groups on opposite sides. That's what makes it the E alkene. So the way we do this is sodium in liquid ammonia with a tert-butyl alcohol solvent. So the mechanism for this is way beyond the scope of this course. But what we're essentially saying is if we have an alkyne and we wanted to convert it to the E alkene, we do have reaction conditions that would allow us to do that as well. So it's just useful to have this in mind as a complementary method for making either the E or the Z alkene from the alkyne instead of having to use elimination reactions. Okay, so that brings us to the end of my lectures. So hopefully I've shown in general across all of these lectures how a knowledge of mechanisms can help us to develop methods to prepare new derivatives. This is useful because often we might have a lead compound that we need to develop further for medicinal chemistry programs, and you'll see specific examples in years 2, 3 and 4 where we look at particular therapeutic conditions. In all cases, I've really tried to emphasise that it's very important to know the stereochemical outcomes because different isomers can have different biological and therapeutic properties, so we always have to be aware of that. Hopefully by looking at these substitution reactions and elimination reactions and reactions of alkynes, I've shown you how we can do some functional group transformations, and that's really going to be useful again as you go forward for making libraries of compounds. If it was easy in drug discovery to just make one compound and take that all the way through into a drug, then we'd probably have lots of treatments for diseases that are currently difficult to treat. It's really not that straightforward. We need to make libraries of compounds so that we can optimize their activities, their stabilities, their selectivities. And again, this is something we build on the course. But by using these types of reactions, we've now introduced ways that we can make libraries of compounds which we can then screen against different biological targets with the ultimate aim of developing new methods for treating diseases and to improve patient therapies. So I'm going to leave the lectures there. You are going to build on this further with Dr. Brazier, where he's going to be looking at reactions of these alkenes, because again, if we can do reactions with them, we can start to introduce further functional groups to make further libraries of compounds. So I hope you found this helpful. Do please look at the videos which I've put up as well to accompany some of those sort of worked examples that we've gone through. You will have a chance to practice this in a workshop, but any questions, please do just drop me an email and I'll be happy to help. Okay, I hope you've enjoyed this and good luck with the rest of your lectures, workshops, practicals, etc. Thank you.